The event will begin in 5 minutes.
سيبدأ الحدث في غضون 5 دقائق.
Ladies and gentlemen, please put your phones on silent.
سيداتي سادتي، يرجى وضع الهاتف المحمول على وضع الصامت.
Please be seated. The event is about to begin.
يرجى منكم التكرم بالجلوس. سيبدأ الحدث بعد قليل.
Please be seated. The event is about to begin.
يرجى منكم التكرم بالجلوس. سيبدأ الحدث بعد قليل.
The feelings I own, the feelings I own, I sense the free. That's all that I need. A long, 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 long road leads me to places I try to find. I don't want to turn back. It leads me to level I go back. It leads me to level.
Hello and good evening, everyone. Well, we only have a few days till the end of WEP, and thanks all for your attendance and engagement throughout all the sessions. We really appreciate that. And as a quick reminder, there is a final gala on Thursday, followed by a panel discussion. We'd like to have all of you here on that day from 5:30 to 7:45 p.m. Afterwards, there will be plenty of fun activities and food for you to enjoy outdoor. Just as a way to say thank you to all of you and to celebrate the end of WEP. Okay, well, for today's panel discussion will be a little bit different. Unfortunately, we weren't able to have our speakers here with us today in person, but we are excited that we can still be connected with them virtually on screen. And the moderator for this session is Professor Mohammed Salim Al-Awaini, who is one of the founding faculty members at KAUST, currently serving as a distinguished professor of electrical and computer engineering. And with that, let's welcome him online.
Thank you very much. Do you hear me? Okay, so I assume that you hear me. I would like to say, first of all, Assalamu alaikum. Good evening to all our students, our community members for this panel part of WEP 2025. For those of you who are following us on YouTube, I would like to say good evening, good afternoon, good morning, depending where you are. So today, hopefully, we have an exciting panel on a topic that is not always covered in details or in a massive way in the news. And I hope that together we'll explore this exciting topic. So we can move to my slides now, please. So I would like to first introduce the panel topic, and then I will introduce the panelists who will give us, based on their experience, their kind of perspective and opinion about the topic that we'll debate today, which is the forgotten race, if you will, or the new space race, which is the race towards exploring the near space. And I will define what the near space means as we progress. Next slide. So, I mean, I'm introducing this in the context of connectivity and 6G, but actually it's beyond that, as we'll see in our discussion. But just, as a way to start, those of you who are familiar with the different generation of communication systems, we are now essentially in the mid of this decade with 5G well deployed in many countries. But from a research perspective, we have been working since the last 5 years on basically beyond 5G or 6G, which of course is going to be about trying to further improve the capabilities of current systems. But what 6G is going hopefully also to address is, next slide, is what is illustrated in this map, where we see a big kind of connectivity gaps, known sometimes as the digital divide or connectivity divide. We are still living in a world where about 1/3 of world population, about 3 billion people, are still unconnected or underconnected. And one of the vision and one of the goal of beyond 5G and 6G network is to close this gap and to connect more of these unconnected. Now, there are many reasons behind that, and correspondingly, there are multiple solutions at different levels. Let's focus here at the technical aspect. And next slide. One obviously way to address this issue, which, by the way, and before actually going into the solution, when we look at trying to connect the unconnected, we are solving many other problems. We are, of course, addressing the core of the problem, which is rural connectivity, hard to reach areas, islands, and so on. But also we are dealing with the disaster type of situation where the network is down and need to be kind of backed up overnight, where basically sometime a natural catastrophe basically leads to thousands of people being unconnected overnight. Exploration in kind of Antarctica or the jungle, and that requires scientists, let's say, to video stream data in real time. IoT device, so Internet of Things device, not only limited to a smart building and smart cities type of paradigm, but basically IoT device everywhere will require this kind of global connectivity, as well as connecting new type of transportation systems, such as flying drones, flying taxi, so-called three-dimensional network, where we don't connect anymore just user on the ground, but user flying at a few hundred meters. This is also a new paradigm that need to be covered as part of connected and unconnected. So we are talking about, yes, rural areas, developing countries, but actually we are solving many other problems. And we will hear from our panelists different perspective on that. So next slide, please. So as you may have heard from the news, one way to bring this global connectivity is by attaching base stations or kind of gateway, if you will, to flying platforms or to space kind of, let's say, satellite type of equipment. And next slide. So probably you are familiar with the different family of satellite systems. Classically, we start with the geosatellite. These are satellites at 36,000 kilometer orbit or altitude. They are geostationary. They have been there for many times, very successful in the context of TV broadcasting. For internet, they offer also service, but they come with a certain latency. As such, more recently, there has been quite a bit of interest in launching this so-called low Earth orbit mega constellation. I'm talking here about Starlink. Well, most of you probably have heard about Starlink, but there is also OneWeb. There is Kuiper in the cooking. The Kuiper is kind of the mega constellation of Amazon, and so on and so forth. So China, of course, has G60 and GW, two other competing constellations. So basically, that's the well-known, let's call it space race, where basically there is many, let's say, companies and countries trying to conquer the space by launching these thousands of satellites to bring global connectivity. Now, what is less known, and next slide, is that there is another paradigm that we would like to kind of present. And this paradigm is motivated by the fact that we live in a world where dense population is not basically binary. It's not like either rural or deep rural with very few people per kilometer square or no people per kilometer square or fraction of people per kilometer square, to basically other extreme, which is super dense downtown urban area with hundreds of people per kilometer square. We live in a world where we have a continuum of dense population, and without going very technical here, based on a stochastic geometry framework, Ruibo Wang, as part of his PhD thesis, showed that actually what works is to have base station at different altitudes, depending on the density population. The lighter is the dense population, the higher you need to go, and eventually probably satellite is the best option. The higher is the density, the lower is the base station, and basically a standard mast or tower in a downtown area will be the way to go. In between, we need to look at basically what we call aerial-based solution. It can be drones, it can be tethered beams or airships, or it can be base station in the near space. And by near space, we are talking about the stratosphere, anywhere between or around 20 kilometers, which is the theme of today's panel. So next slide. So we would like to talk about the near space. Yes, next slide. Yes, next. So we want to talk about the near space, and within the near space or the stratosphere, roughly 20 kilometer altitude. By the way, the airplane we take fly typically at 10 to 12 kilometers, so we are much higher than that. It's a nice sweet spot from a kind of a wind and pressure perspective. This space or this near space, we can use there this kind of platform. They are known as HAPS. HAPS stand for High Altitude Platform Stations. Sometimes they are known as High Altitude Pseudo Satellite. They come in different forms. They can be coming in the form of balloons, airships, or basically fixed wing aircraft or gliders. And part of their mission is to bring connectivity when we attach a base station to them. Next slide. So the vision is kind of illustrated in this infographics, just to kind of, let's say, emphasize that it's not only a connectivity problem. Connectivity is one aspect of HAPS. HAPS is an aerial infrastructure that is there to allow us to kind of be present in the stratosphere or in the near space. Here in this infographics, we are showing in green, basically HAPS providing connectivity to people, like it happens here that we are looking at a disaster, a flood basically. So people have been moved to a refugee camp, and you need to bring connectivity on the fly. And there is beams that are there, as you see here, trying to help these people connect. But also this HAPS is providing connectivity to this IoT device in a smart agriculture environment. But HAPS can carry a payload that has also a camera that can be used for border control, a LiDAR that can be used for environment monitoring, a radar to, let's say, look at the level of water. So basically, it's again an infrastructure in the basically stratosphere that can be used for multiple missions depending on the need. Next slide. So today panel is going to focus on these HAPS. And by the way, we are not about a single HAPS, like we talk about a constellation of satellites. We talk about a constellation of HAPS or a fleet of HAPS. Together, they can cover hundreds of kilometer squares, and they can provide not only connectivity, but I say multiple other missions. They can be interconnected through free space optic links, and they can be backhauled through, again, backhaul link to satellite network or to the ground network. So today we have a panel that is going to tell us a little bit more about this exploration of the stratosphere, how it's done, where is the state of development of these HAPS, what is the business case for that. So next slide. This is a little bit my research group at KAUST that kind of carry this kind of research, and we have a UNESCO chair focusing Connect the Unconnected. But I would like now to kind of introduce the panelists that are basically going to tell us more about this stratosphere exploration or near space explorations and HAPS. We start with Professor Halim Yanikomeroglu from basically Carleton University in Ottawa, distinguished professor from Carleton, who will tell us basically an academic perspective on HAPS and how they are going to be used, not only for connectivity, but also for many other applications. And in connectivity per se, as a telecom architect, what is the benefit of using HAPS? Then we'll move to Shiro Fukumoto-san from SoftBank Japan, who will tell us a little bit why SoftBank, one of the major mobile network operator in Japan, actually I would say in the world, is interested in HAPS and investing heavily in HAPS, and what is the business case of these HAPS, and also more generally the use of of stratosphere. Now, of course, HAPS come with some challenges, in particular how we can make them reliable, how we can minimize basically accidents, especially when they take off and they land. And here we have Dr. Paul Stevens from Voltitude, who specializes in basically monitoring the stratosphere, and he'll tell us a little bit more about his expertise and how this hopefully will help down the road the operation of these kind of constellation of HAPS. So Voltitude is a company based in UK, and Paul will tell us a little bit more about him and about his company. And finally, we have Dr. Tom Nugent from PowerLight, another interesting company based in near Seattle in the US, who will tell us how we can address another important challenge that HAPS face. One of the challenges that HAPS face is basically how do we power them? How can we generate power at 20-kilometer altitude? We need this power just to make sure that the HAPS basically have enough power to basically fly or stay for long duration in the stratosphere, but also to basically give power to all the kind of device we would like to use. We would like to use base station, we'd like to use radar, we want to use cameras. All of these devices need power, and he will tell us about a little bit science fiction, maybe now, basically perspective on how we can power these HAPS. But I think it's very interesting approach, and maybe that's the approach that we'll be using 20, 30 years down the road. So with that, I will give the floor to my colleague and dear friend, Professor Halim from Carleton University, to give us his perspective on HAPS and how HAPS can be a disruptive technology.
Thank you very much, Professor Al-Alwani. It is such a delight to be a part of WEP 2025 program and also this distinguished panel. I am Halim Yanikomeroglu from Carleton University in Ottawa, Canada, and I lead the non-terrestrial networks lab there. Today's discussion item is a very interesting forward-looking construct. We are talking about a new infrastructure in 2030s and beyond between the terrestrial infrastructure that we use on an hourly basis or even more often with our smartphones and so on, and also the space infrastructure. Those are the satellite networks we are also very familiar with from the popular media. Here the discussion is a new infrastructure in between. Next slide. As Professor Alwani mentioned, the connectivity world is now busy about the standardization of the next generation mobile networks. That is 6G. Standards will be coming around 2030 timeframe. A very important pressing point is, what will 6G bring as a novel item? Obviously, there will be incremental increase in the legacy KPIs, such as better rates to your smart device. But the more interesting part of 6G is arguably the upper part of the wheel diagram. And there you see the new capabilities of 6G. Among them, perhaps the most important one is ubiquitous coverage. So we would want our smart devices, that is today it is smartphone, but tomorrow it might be a smart glass, to be connected opportunistically to Wi-Fi network when you are in indoors, or a macro base station or a small base station when you are out, or opportunistically to non-terrestrial networks. So if we want that ubiquitous connectivity, then we cannot really do that with the terrestrial network alone. Non-terrestrial networks will be an integral part of future generations of our connectivity infrastructure. Next. Basically, the first 5 generations of mobile networks brought mobility. The device itself got enhanced progressively, and applications as well. In the beginning, it was a phone, it became smartphone. Tomorrow it will be a XR, AR type of device. But with 6G, a new era is starting. I refer to that as the second revolution in the wireless domain, and that is to be connected everywhere, whether you are on the ground, in the air, offshore, in such a way that your device should operate like your watch. You never worry about whether your watch will work if you are in the city or on the plane or offshore. We want a similar thing for our connectivity. And obviously what we are discussing here is very different than satellite communications for rural and remote. First of all, non-terrestrial networks is more than satellites, and today we are discussing near space. It is more than connectivity, as Professor Alwani alluded to, and I will unpack in a moment. Opportunities are very many, including surveillance, reconnaissance, intelligence, imaging, sensing, and so on. And this is not only limited to rural and remote. We are talking about connectivity everywhere. Therefore, it is really a paradigm shift. This discussion is not only about rural and remote, but a global market of 10 billion smartphones, maybe 100 billion devices of all sorts. So a $10 trillion market, and it gives some global power, actually, whoever has access to this global network and customer base. Next slide. I will now try to differentiate HAPS, that is high altitude platform stations at around 20 kilometers, from the more familiar satellite networks. To give a perspective, even the closest one of satellites are at 500 kilometers. So first and foremost, HAPS is very close, meaning that much more stronger signal, meaning that pretty much any application you can run with a terrestrial network, you should be able to run through HAPS as well. 20 kilometers line of sight is not that far away. And then the very fact that HAPS is not orbiting, it is stationary for all practical purposes, comes with a lot of technical advantages, and including data sovereignty and data security. But also, you don't need a big fleet of constellation to start with. If there is a need in the Jeddah area, HAPS can be deployed, and as the need progresses, another one can be put, for instance, in Riyadh and Mecca, and they can be all connected. Launching is very straightforward. Just from a field, you don't need a rocket. As I mentioned, since this is a big infrastructure, there would be other benefits than, in addition to connectivity. Imagine massive cameras mounted in these platforms for surveillance and other purposes. Again, in addition to rural and remote, there would be big advantage to deploy these networks in urban areas as well. Next slide. We all know the impressive growth of LEO mega constellations. Starlink comes to mind, but there are other big projects as well. Kuiper, Amazon had its maiden launch just a few days ago. So if we fast forward in about 10 years' time, these mega constellations will be so powerful that they can carry a mind-boggling amount of global wireless traffic. But under the assumption that if the signals can reach to the customer device, the major roadblock here is due to the sheer distance, the incoming signal would be very weak. So to make this humongous potential capacity a reality, one possible solution is to deploy a relay network in near space composed of HAPS mega constellations. So rather than satellite direct to device, we can have satellite to HAPS to smart device connectivity. Next slide, please. And without derailing the discussion too much, here I am giving an example from surveillance, reconnaissance, intelligence framework. This is super important for urban areas. Today's spy satellites have resolution about a few 10 centimeters per pixel. But if we bring this technology very close to Earth with much bigger infrastructure, by the way, a HAPS can be much bigger than a LEO satellite. At some point down the road, it might be possible to see the faces on the ground. And you can imagine the consequences of such an infrastructure. Next slide. Another example is sustainability and energy consumption. Today, we are throwing infrastructure so that a user is always close to an access point, but most of the time, many access points might be idle, very high capex, very high opex. Next slide. A much better way to do this is through spot beams from near space. Whenever there is a need for connectivity, the spot beam can be turned on, do the job, and turned off again without contaminating the environment with unnecessary radio waves. Next slide. So in the skies of Jeddah, maybe in 2035, 2040, we might have a cluster of HAPS interconnected with each other with ultra-high speed free space optical links with a variety of beams, very narrow beams for hotspot creation, very wide beams for IoT data collection, and all other applications like navigation, localization, and others. Next slide. And here is again a cluster of HAPS in the skies of Jeddah connected to another HAPS cluster in the skies of Mecca, and they are all connected with free space optical, and all of them again connected to the satellite networks. Next slide. I am just wrapping it up. We are entering to very exciting times. President Trump took office just yesterday. He is a disruptive individual, and there is an alliance with Disruption 10X, if I may say, that is Elon Musk. And now, if in the coming years, AI and quantum also is in the picture, this is an unprecedented power localization, if I may say, and similar things might happen in other jurisdictions in China and elsewhere. So it is really an exciting times how this story will unfold. Next slide. And this is my conclusion slide. When we say NTN, it is more than satellites, it is more than rural and remote. This is a humongous market, and this is a new infrastructure with unprecedented potentials. In the beginning, it will start as complementing the terrestrial architecture, but when NTN, non-terrestrial networks, is powerful enough in, let us starting mid-2030s, we might see very interesting scenarios. For instance, if satellite networks and near space networks give hand in hand, do we really need the terrestrial network and terrestrial operators as we know today? Or if terrestrial networks make alliance with HAPS networks, do we need satellite networks as big as they are becoming today? We will wait and see. All these exciting developments will not happen in just a couple of years. This is a roadmap towards 2050, will happen progressively, but for sure it is transformative and for sure it is disruptive. Thank you.
Thank you very much, Halim. Very interesting perspective. Let's now give the floor to Shiro from SoftBank in Japan, and that he share with us his perspective on the near space and HAPS development in Japan. Go ahead, Shiro.
Okay, thank you very much, Professor Arawini and KAUST for giving me this excellent opportunity. My name is Shiro Fukumoto from SoftBank Corporation. And SoftBank is one of Japanese mobile network operator providing the mobile service with 40 million total subscribers, including 31 million smartphone users. In this presentation, I show what NTN should be the MN's point of view and introduce our focus, HAPS, current development status and regulatory point. So the next slide, please. Yes, and this slide shows the current mobile network deployment in general. We are deploying a seamless network, including the indoor and underground, using various types of base stations, like tower building rooftop type and indoor type, depending on the population density, building, traffic, and so on. And we have spent much investment and time for deploying current network, and we are continuing to evolve it, including introduction of 5G with various frequency bands like 700 mega 1.7 to 3.5, 30.9, and 28 gigahertz. Sometimes we heard concern from MNO that NTN will become a business competitor, but we don't think so. At least, it's not possible to cover urban and suburban area with only NTN, and it's essential to continue deployment with ground-based stations. Next slide, please. Yes, so question here is, we don't need NTN? The answer is no, we need NTN. We are using NTN actually, mainly GEO FSS so far as base stations backhaul links to cover rural area and disaster recovery. Next slide, please. But in the future, direct-to-device D2D is especially important. The current satellite solution is not very adaptable because satellite terminals basically required dedicated one, which many people do not have. On the other hand, D2D will be possible to connect using a normal terminal such as smartphone people already own, even in that area and in case disaster. So NTN should work for complementary in the entire mobile network. And NTN can also provide 3D coverage to the sky, including existing cover area. This will contribute to new mobile networks such as drone. Next slide, please. Yep, component of NTN. We can consider HAPS, LEO, and GEO satellite in general. Next slide, please. But among NTN, we think LEO and HAPS can only achieve direct connect to regular smartphone, I mean D2D. Actually, D2D with GEO may also be worked to some extent. For example, some Android smartphones have messaging function through GEO satellite right now, but given the longer latency and low data rate in the, rather than LEO, it's unclear whether GEO will be one of the components of D2D, considering the entire mobile service. Next slide, please. So what is important here is to capitalize on unique characteristics of HAPS and LEO. In other words, HAPS and LEO can complement each other by taking advantage of their different characteristics because there is no single perfect solution. So next slide, please. Among NTN, we focus on HAPS. From here, I'll explain about our effort towards HAPS commercialization. Yeah, here is our main vehicle. It's called Sunglider. This is a huge aircraft with 79 meters wingspan. And we are jointly developing this big aircraft with a US-based aviation vendor called AeroVironment. And ultimately, we are aiming for continuous flight of more than 6 months after takeoff. Next slide, please. Yep. This slide shows the technology supporting the realization of HAPS. Aircraft must be lightweight and durable to the stratospheric environment, such as low temperature and low atmospheric pressure, to enable long-term flight. And similarly, communication equipment, I mean the communication payload, must be capable of adapting to stratospheric environment and shall also be designed not to cause interference to the ground network. And the right side, fundamental technology that make up the aircraft lightweight, high performance, and cost effective. Among them, we are particularly focused on the development of solar panel and batteries and motors as well. Some technical development work on telecommunication payload, solar panel, battery is being funded by Japanese government. Next slide, please. Yeah, here's the status of aircraft development. In 2019 to 2020, we have successfully done multiple flights on 4G LTE communication test in United States. And 2023, we have conducted the world first 5G communication test from the stratosphere in Rwanda. In addition, last August, our partner, AeroVironment, conducted a flight test with the same type of our HAPS together with US Department of Defense. So based on data acquired in these tests, we are continuing the development of our aircraft. Next slide, please. In addition, we are developing a communication payload to locate on HAPS. Cylindrical antenna capable of precise beam control through digital beam homing. Actually, we demonstrated this antenna field trial with tethered balloon last year and confirmed that ability to maintain a constant footprint work well even when the balloon is moving unsteadily. In addition, as a course of our R&D program, we plan to conduct free space optic communication between HAPS and LEO satellite in 2026. In case where ground-based backhaul link are not available, it is important to ensure site diversity by using satellite to provide HAPS backhaul link. And instead of radio waves, use of wireless optic will contribute to more flexible implementation of HAPS because no regulatory procedure will be required. And these R&D efforts are also based on government funding. Next slide, please. Yes, next slide, please. Finally, I brief the international standardization and regulations. Here, HAPS-related topics discussed in ITUR, ITU-D, and 3GPP. In ITUR, HAPS was discussed as component of 6G, IMT 2030, and these elements can be seen in the technology trend report and the concept recommendation. And 3GPP Release 17 specified HAPS can be treated as a normal terrestrial base station. This means that both base stations and terminal can be used without any changes to the 3GPP specification. This is a major feature or not found in other MTN solutions. Next slide, please. Regarding international HAPS regulation, frequency of 7 to 900 MHz, 1.7 to 2.1 GHz, and 2.6 GHz were added for HAPS in ITU WRC 23. Actually, 2.1 GHz had been available from the past, but it was not possible to use such as uplink or 1.7 GHz, downlink or 2.1 GHz combination, which are widely used in America, for example. So This regulatory change provides flexibility in the use of HAPS frequencies, including combination with these frequencies, and also establish regulatory conditions to avoid interference to neighboring countries. So we hope this decision will facilitate introduce of HAPS in various countries. Next slide, please. Yeah, this is the last slide, and I have introduced our company HAPS initiative. There are still many challenges that need to be overcome before this large scale of HAPS can be commercially deployed. As a quote of this slide, today's challenge will be tomorrow's normal. So we'll continue our activity in the belief that it will be normal to be HAPS in the future. That's all. Thank you very much for your attention. Thank you.
Thank you very much, Shiro. Very interesting. So let us now move to Paul. Paul will give us his perspective on actually the stratosphere near space and what kind of work is being done to characterize condition there and how this can help the operation of HAPS in the future. Paul, the floor is yours.
Thank you, and good afternoon. My name's Paul Stevens. My background, insofar as I'm connected to the stratospheric industry, is that I've worked for 25 years on developing HAPS technology. Until 2020, I was head of design at Airbus on the Zephyr program. I'm delighted to say that Zephyr is currently flying out of Kenya. I noticed it had taken off just 2 days ago. So if you look on flight radar, you might see that aircraft airborne. But in 2020, I started Voltitude Limited in the UK. Its purpose was to develop innovative new technologies to address challenges which I felt were holding the industry back. And that is the topic of my presentation, how we can accelerate the industry and overcome the challenges. So next slide, please. So a little bit about how fixed-wing solar-powered planes work. The high-altitude pseudo-satellites, or HAPS, they work by flying in the stratosphere on solar electric power. During the daytime, they charge high specific energy density batteries, which are used to power all the systems and continue to cruise in the stratosphere all through the night until the following morning, where the solar power returns and the cycle repeats. The HAPS aircraft stays in the stratosphere provided an important energy budget can be balanced, and that is that the total energy collected and stored on board the aircraft during the day is greater than or equal to the total energy consumed overnight. A very simple energy budget, a bit like an accountant's budget. And so flying through the night on stored energy is the challenge. Next slide, please. So to highlight how significant this challenge is, because I'm sure many of us have flown through the night on a commercial jet aircraft, having the luxury of a very high energy density fuel powering that aircraft. So this diagram here shows the trends in different types of fuel that is used in aviation, and it shows energy density, so watt hours per litre on the y-axis, and on the x-axis it shows the specific energy densities, that's watt hours per kilogram. And I've highlighted aviation gas, which is it's very similar to diesel, and it has an energy density of 12 kilowatt hours per kilogram. And that's how we fly for so long around the planet on our commercial airlines as we go on holiday. Contrasting that with the energy density of battery technology, so here we are in 2025, and the best commercially available batteries in the world are just about achieving 500 watt hours per kilogram. Contrasting that with the 12 kilowatt hours for aviation gas, we see that the energy density of batteries is 25 times less than aviation gas. So this highlights the challenge. We've got to design aircraft that can fly all the way through the night, in winter where the nights are longer as well, only on energy stored in high specific energy density batteries. And so how do we do that? We do that by designing aircraft that have very low power to cruise, Or we look to new technology to perhaps beam power to those aircraft. But I won't steal the thunder of our next panelist. So please move on to the next slide. So I'd like to next introduce a new part of the puzzle as to what the challenges are. So we've talked about energy density. This slide is about the Great Flight Diagram. So this is an important principle or statement or trend in aviation. The Great Flight Diagram is very useful to help us to understand all that has happened before us. What is possible in the history of aviation, including manned, unmanned, and flying animals. What we have here plotted on the y-axis is the weight of the flying system, and on the x-axis we have the cruise speed, or sometimes referred to in some incarnations as the wing loading, the mass of the aircraft per wing area. And you can see I've highlighted certain types of aviation within there. There are insects in yellow, there's birds in green, and there's manned aviation in blue. And we see there's a trend, a line. It's a linear scale, and there is a linear relationship when plotted in these axes. And that linear relationship tells us something that's irrefutable, that's undeniable. And that is that in aviation, there are certain rules that must be abided by. And we see that all that has flown before us successfully in nature and commercially since the advent of manned aviation are bounded by two limits. There's a right-hand limit, in which defines a place where there is no longer a fuel with a high enough specific energy density that exists to provide a useful endurance for types of aviation beyond that right-hand limit. And similarly, on the left-hand side, there is a left-hand limit which defines flying systems which are too fragile to succeed in the real world. They are too slow, too large, too flexible, and too lightweight. And so if you think about it, I've highlighted solar flight, solar-powered electric flight, and human-powered flight. So these are the athletes that cycle very hard in their machines to get airborne and fly. I refer to these sometimes as unnatural forms of aviation because they're not able to fly frequently enough in the troposphere, where the weather systems exist, to allow them to be commercially viable. So it paints a very bleak picture for solar electric flight, but there is somewhere where we can fly safely. So next slide, please. So where on earth can solar electric aircraft fly perpetually? I've talked about the Great Flight Diagram highlighting that they are an unnatural form of aviation with regard to the troposphere, which is the part of the atmosphere we live in, where all the weather systems occur. But above the troposphere is the stratosphere, and that's divided between, separating the troposphere and the stratosphere is the tropopause marked on this diagram. And what we see is that in the troposphere, which is characterized by strong weather systems, strong convection, we don't see anything like that in the stratosphere. It's a very benign environment, a very safe environment. And we find that that environment is very forthcoming to the type of aircraft that would otherwise not be suitable for long duration flights in the troposphere. And so I've indicated a mean time between accidents due to turbulence on this diagram to show how those vary with altitude for solar planes or planes designed for solar flight. And we see that unless we very selectively control the conditions for flight, we see that the viability of those platforms decreases the lower in the atmosphere they fly. But it is years, measured in years in the stratosphere. And I should say it's a safe place, but it's not without hazards. There are mechanisms by which hazardous weather phenomena can propagate up from the troposphere into the stratosphere. And that brings me on to the next challenge for the industry, which is better weather forecasting. So next slide, please. So in the 1980s, numerical weather prediction modeling came of age, and this has become increasingly sophisticated with higher resolution forecasting possible. However, the models are only as good as the observation data used to initialize them. The map on the left shows where all of the radiosondes are launched each day. These are weather balloons sampling the atmosphere in very high resolution. And you'll see that there are huge gaps over the oceans, remote areas, and poorer countries. So this is a problem because there is a sparsity of high resolution, high quality data to initialize the weather prediction forecasting models. They are assisted by space-based observations, but space-based observations lack the vertical resolution to provide really fine forecast. Furthermore, on the right, we see a depiction of the levels, the altitude levels in global forecast models. And we see that in the lower stratosphere, between 50 and 80,000 feet, there are actually only 15 levels in the highest resolution global models. This means that they lack the resolution to predict some of the finer details, missing wind shear and wind direction details that are critical for safe navigation and efficient constellation management of stratospheric platforms. Next slide, please. So my company's been developing some solutions to these challenges, specifically micro dropsondes, which we can dispense from stratospheric platforms to provide really high resolution data of the entire lower stratosphere and the entire troposphere. We currently use these to help forecast extreme weather phenomena, specifically tropical cyclones. And this is a snapshot of this balloon system carrying micro dropsondes across the Atlantic, which is a particularly data sparse area. This sort of technology stands to greatly improve weather forecasting for the HAPS industry. Next slide, please. But to fly, as I've said, to fly persistently on solar power in the stratosphere requires an aircraft with exceptionally low power to cruise. This means viable designs fly extremely slowly. They have large wingspans with high aspect ratios, and their structures are so lightweight that they display strong aeroelastic properties, which means they bend and deform when encountering gusts and turbulence. This makes them very vulnerable, particularly when flying in the troposphere, getting to and from the stratosphere. The problem is so bad that the industry is currently suffering from a platform loss rate of about 1 in 3 missions. So Voltitude's been investigating a new type of gust alleviation system to make the operating envelope much larger for this type of aircraft. We've been test flying this technology, and pleased to say that we've been able to show that we can double the speed envelope of these aircraft without the planes crashing. And this is really critical to expanding their availability, reducing their costs, and increasing safety. Currently, we're using this type of technology to showcase a new weather data gathering solution by dropping tiny dropsondes weighing just 20 grams from this aircraft in a very targeted manner over remote regions to help reinforce the forecasting of extreme weather. And this is a key technology for the wider industry. We all need to work together to share data and help define a better forecast for the stratosphere to help us all navigate better. So next slide, please. So in conclusion, I've introduced two of the main challenges. One is the need for aircraft to be more robust in their ability to get to and from the stratosphere, make them safer, and also to collect new sources of data, high resolution data, to feed into weather models to give us a new type of forecast product targeting the stratospheric HAPS industry. Thank you very much.
Thank you very much, Paul. It was very clear, and I think we learned a lot from your presentation and from the state of the art, basically, in terms of making HAPS safer and more, let's say, with a longer endurance. So now let's move to the last presentation before we go to the Q&A part of our panel. And here I would like to give the floor to Tom from PowerLight company. Go ahead, please, Tom.
Great. Thank you. And thank you for inviting me to this. And today, as Paul hinted at, I'm going to talk about power beaming to overcome some of the limits that the stratospheric platforms encounter. Next, please. So one of the things about unmanned platforms, whether they're in the stratosphere or elsewhere, even though they're touted as being autonomous, they currently require people to interact with them very regularly to change batteries or to charge them. And what we are proposing with power beaming is a system where these autonomous systems can be autonomous and they can, fly within range of charging stations where they can just automatically be recharged and not require continual babysitting by humans. Next, please. The way that laser power beaming works is that we take energy somewhere where it is more easily accessible from the grid that you plug into a wall outlet or a generator or a solar farm. And we convert that light or that electricity into light using lasers. And we shape that light and then project it over long distances to special receivers that use photovoltaic cells, sort of like are found in solar cells, but tuned to the laser wavelength to convert that light back into electricity, where it can then be delivered to whatever device needs it. And we operate in the near infrared wavelengths, just sort of beyond where people can see, but things like where your TV remote or a lot of telecommunication devices operate. Next, please. PowerLight has been developing this technology for 15 years now and has built numerous hardware systems and has delivered power up to 1 kilowatt of electric power out at receivers and have delivered power repeatedly at distances of 1 kilometer and are working right now to extend that to even longer distances. And many, but not all of these demonstrations have been for flying aircraft, which, as others have pointed out, have severe limits on weight. And so trying to make these power beaming receivers have a high power to weight ratio is important. I'll talk more about that in just a minute. One of the things briefly that people sometimes ask about is safety. And one of our technology differentiators is our active sensing that detects objects approaching the beam to turn the laser off before anything can get exposed to that. And it's been certified by independent organizations as fully safe for people to be around without needing any protective gear. Next, please. So this chart shows all of the different demonstrations for power beaming, both using lasers and microwave, that have been done around the world over the years. And this log scale sort of shows the kinds of power that have been delivered and the kinds of distances. And a number of them have been out approaching the kinds of distances that are needed here. So if you click next, please. For the areas that we care about for power beaming, this higher power, higher distance range is really what's of interest. Next, please. So this sort of zooms into that power levels greater than 100 watts and distances greater than 100 meters. And as you can see, a lot of the work being done so far in this area has been done by PowerLight. And we can see to the right here the kinds of distances and power levels that are needed for these HAPS vehicles. In discussions with HAPS providers, it's clear that even small amounts of power, a couple hundred watts, can be useful for extending their flight and their capabilities. But as they look to the future to having bigger, heavier payloads that are more power hungry, those power demands we expect to go up significantly. Next, please. So one other thing to look at for flying, and others have talked about this sort of difference of the way you're carrying energy, is any energy system is competing for your mass budget on your vehicle in terms of your payload, the thing you actually care about of your, in this case, communication or sensing devices, and how long you can fly. And combustion engines, as we've mentioned, have a high power to weight ratio. You can carry a lot of payload in vehicles with them, but they don't last very long because eventually the fuel runs out. Next, please. And the same thing is generally true for fuel cells that operate again, with a chemical reaction. Next, please. Batteries have improved quite a bit over the last 15 years, nearly doubling their energy density. But even the sort of right-hand vertical line there are still very low in terms of what they can achieve for energy density compared to some of these other options. Next, please. As Paul pointed out, the solar electric aircraft, by the nature of sunlight not being available all the time, plus needing to carry a large amount of low energy density batteries, have a very low power to weight ratio. And that forces them into this sort of gossamer design that, as Paul mentioned, is very fragile and often can't carry a lot of payload, but they can fly practically forever. Next, please. Finally, optical power delivery via laser power beaming can get the best of both worlds. It's already been shown to have a high power to weight ratio and has been shown to fly for extremely long periods of time. Next, please. So looking a different way at these challenges that HAPS vehicles encounter, we can look at the, in this case, incident sunlight available around the world, ignoring clouds, across the globe versus the time of year. And clearly, if you're near the equator year-round, you can get a reasonable amount of sunlight average over a 24-hour period. But as you go into higher latitudes, and especially in the local winter, that energy or that power density from sunlight falls very low, by a factor of 8 nearly. And that's just the incoming sunlight. You then have to convert that sunlight with solar panels that have their own efficiency hit. Next, please. Oh, I'm sorry. Click next as well, please. If we look again at the power per weight, which is the vertical axis, that's again that sort of weight of your energy system. But if you look at the power per area, solar arrays, again, averaged over a 24-hour period, not sort of instantaneous, have 3 or more orders of magnitude difference in how much power you can get per area. And so when you have the entire tops of these large wingspans covered with power, you may be getting hundreds of watts, but you could get that same amount of power from a laser power beaming receiver that is much smaller, takes up one small section of a wing. And so this will enable these much higher levels of power for the same footprint that is available for power on these aircraft. Next, please. So in summary, laser power beaming is actually much closer to reality than it is science fiction nowadays because of work by a number of groups. We've shown that it's safe and can reach to useful power levels and useful distances. And if you're interested in learning more, there's a book that I'm a co-author on that was published last year. Next, please. Next. Yeah, there we go. Thank you. And that's all I have to say. I'm happy to answer questions. Thank you.
Thanks. Thanks a lot, Tom. Very instructive. So now that we heard from all our panelists, let's try to see if we have questions from the audience.
Yes, so if anyone has any question, please use any of the 2 microphones. Thank you. Anyone? Okay. No questions? Okay, so I do have some questions, so let me kind of ask my colleagues here some of these questions. So my first question, and this is to all of you can comment on that. So, those of us who are active in this area of HAPS in general, we know that there has been quite a bit of interest in doing proof of concept or demos. Shiro talked about some of them. So these demos have been done with 4G and 5G.
showing the ability to connect, a standard phone to a kind of a base station attached to a HAPS. But the question I'm asking is, when are we, we have been talking about HAPS for the last, let's say, maybe more than 10 years, at least with the well-known Facebook and Loon Google project. But when do you think that HAPS is going to become a reality? Obviously, I think Halim kind of mentioned a little bit that this is not really going to be part of, let's say, the near future, the 6G, like the 2-3 years down the road. But how long are we to wait? I heard that in Japan, maybe it's going to be deployed early on as part of post-disaster emergency communication. So I would like to hear your perspective on when do you think HAPS are going to be part of our ecosystem? Who would like to start? Halim, do you want to start on this?
Sure. Obviously, my colleagues from industry would be in a better position to address this. And I would like to hear what they will be saying. But here is my comment. There are two possibilities. One of them, the linear progression. HAPS concept has been around for decades, actually, for weather monitoring, ozone monitoring, scientific purposes. Obviously, when it is connectivity, it is a much different, precise discussion. So it will continue progressing, and then it might still take a while to have the envisioned aircraft types. But I am expecting actually disruptive developments, very much like powering with a laser. Basically, if you look at the satellite industry, the big investment made by SpaceX was a game changer. So if in the coming years such big investments become a possibility in the near space domain, I think we will see much more rapid than linear progression. This can be a reality as early as early 2030s. That is my take, Professor Alwini.
Thank you, Halim. Shiro,
Yep,
what is your
thank you.
perspective from a Japanese, let's say, point of view?
Yeah, actually, I think we think the commercial progress of HAPS is not so slow. Yeah, actually, some country, including some Japanese company, considering the early commercial introduction in 1 and 2 years. This means that you can see the actual commercial HAPS in the near future. But on the other hand, actually HAPS airframes, not aircraft, come in a variety of types, including the heavier than air, the fixed wing, and lighter than air, balloon and airship. And not all type, including payload size, ready for early commercial introduction. For example, our case, Sunglider, large fixed wing solar plane with big payload capacity required. It generally takes time from both technical and regulatory perspective before large-scale commercial introduced. Currently, we are working to realize this large size of aircraft to finish our research and development by 2027 and to try to commercialization after that. So maybe the rate of 2020s or 2030 is a practical timing to see the commercialization of HAPS around the world. Thank you.
Thank you, Shiro. Paul, Tom, any input or suggestion on this issue?
Yes, I think there are some niche industries which can benefit from the current status of HAPS, both lighter than air and fixed wing. And I think the challenges that we've all been discussing are going to be resolved. But some of lighter than air technology is already delivering military service capabilities, and we are beginning to see some solar electric fixed-wing aircraft operating under very specific conditions and specific missions. But I think we've all talked about it, but to really open up the civil potential for commercialization of this technology, we've got to address those key challenges. And I think, though, that's going to change very quickly. And I agree with my colleagues here that I think 2030 to 2035 is the time frame for which we'll see the disruptive technologies coming to the forefront and enabling new commercial services from the stratosphere.
Good.
Thank you.
Tom,
I don't have any particular insight into the HAPS, but PowerLight is working to bring our first power beaming product to market in the next few years for the smaller Group 2 drones. These are the ones that might have a wingspan of a few meters and fly at altitudes of maybe a kilometer above the ground. And I think that those kinds of smaller platforms might see some early use as these communications relays at the lower, smaller coverage areas that can feed into the growing demand for this connectivity. And so I think there may be a pathway from the smaller drones up into this sort of 2030 beyond timeframe that the other panelists have suggested for when the HAPS will be commercially available.
Excellent, very good. Shiro, given your interest in regulation, and by regulation I mean here the spectrum regulations, can you comment on the possibility of having interference problems, especially between neighboring countries if spectrum coordination is not happening between these countries? Given the large coverage that HAPS can offer, there is obviously some concern that this can lead to some interference kind of affecting let's say front region in the boundaries between different countries. Any kind of insight on this particular problem?
Yeah, thank you very much. It's a very good question. Yeah, because I was working for such international regulation for long years, and actually the international regulation, I mean radio regulations, clearly specified the technical conditions to avoid interference, as I mentioned in my presentation, as a result of WRC 23, and this regulation clearly mention about power limitation, such as power flux density limitation as a hard limit, or coordination threshold to avoid any interference generated by HAPS transmit frequency band. So that even in the not coordinated case, HAPS operating in certain country can avoid interference by complying with this radio regulation. So that's why I think this kind of the new regulation will contribute to introduce HAPS in various countries. Thank you very much.
Very good. It seems there's a question from the audience, but
yes,
before giving the hand to the audience, now I want to have a follow-up question, and then I will go to the audience because they are connected. And I think Halim will be the best person to answer this question in relation to the spectrum allocation and what happened in the ITU World Radio Congress in 2023 with all of these terrestrial frequencies being assigned also to HAPS. We want to know how coordination can happen and actually how HAPS can offer in a way an interesting kind of perspective on the so-called direct-to-device. You mentioned that, Halim, in your talk. This so-called direct-to-device paradigm that all the satellite companies are trying to solve, and how HAPS can actually solve this question or this issue in a very nice way, given now that spectrum has been allocated to in a way that it is kind of harmonized with the terrestrial spectrum allocation.
Yes, Professor Alwani, extremely important question. Just for our students' information, in this big ecosystem, there is the global regulator, that is the International Telecommunications Union, which makes the frequency assignments and so on. And there was a recent, very important development Long story short, now my smartphone, if there were a HAPS network, can connect to HAPS network or to terrestrial network. This is an important step forward. Now, we really want this ecosystem going beyond niche applications. Those niche applications around rural and remote and so on, those are important, but that also becomes a roadblock in terms of making a business case. Therefore, for that global connectivity, direct-to-device is very important. Our friends have already mentioned some other roadblocks like, for instance, long-endurance aircraft and energy. From an ICT, information and communication technologies viewpoint, probably the most important challenge is interference management. So these base stations otherwise in near space can result in interference shower and might have a very bad impact. So AI and advanced antenna technologies, in my view, will play a tremendous role in managing interference. Direct to smartphones is very viable from near space. And my expectation, finally, is that by 2050, we will have around 10,000 to 100,000 HAPS around the globe, including urban areas beyond connectivity, like reconnaissance and other purposes. And really, our creativity is the limit. Imagine a time, 20 years' time, there are drone highways in urban areas. How do you give navigation control? I can't think of a way better than deploying a HAPS on urban areas.
Very good. Thank you, Halim. Now let's go to the auditorium because I think we have a question from the floor.
Yeah, we have one more question. Please go ahead.
Hello, thank you for all the presenters for insightful presentations. My question is inspired by the satellites in the low Earth orbit and the Chancellor effect, where there's a chance of those satellites colliding, destroying each other, and creating a chain reaction where the whole infrastructure is potentially destroyed. So when we speak about, of course, aircraft flying within the airspace, the chance of them colliding midair is very small. Due to the sheer vastness of the airspace. But, for example, commercial flights have very precise and strongly controlled systems of air traffic control which ensure that they're flying on a schedule with certain distances and so on. So my question is, if we have whole fleets of these telecommunication aircraft, can we ever make this system truly autonomous without any human interaction? Are we able to make them like autonomous, like self-driving cars, fully let them make all the decisions and coordinate with other aircraft? And is there even a need to make them fully autonomous, or is it okay, like with air traffic control, to have several people stationed around the globe, just overlooking the system and controlling it?
Excellent question, actually, very relevant. Anyone wants to answer this question?
Yep, from operator side. Yes, thank you very much. Yeah, good question. Yeah, actually, the air traffic control is a very important topic, considering the to be a HAPS operator, if you want. And then SoftBank is actually a terrestrial mobile network operator, but we want to be a HAPS operator in the future. At that time, it is very important to who will control aircraft. And the current regulation must need one aircraft, one pilot. It's a very inconvenient, considering the scalable operating or future HAPS. In that case, we need to consider about the both side, system and regulatory side, to efficient control multiple aircraft with multiple pilot, and also in the future, autonomous pilot. So the firstly, the one vs one pilot aircraft is need to control aircraft, but in the future, M pilot, number N aircraft control is must be regulated for the aviation law, and also the autonomous pilot should be including. Otherwise, it is very difficult to realize the full scale or high scale of the HAPS operation in the future. Thank you.
Thank you, Shiro. Maybe we have time for one extra question, and this is addressed to Paul. It's also like related to safety, and you mentioned during your presentation that most of the accident, and from what you said, there is like 1 chance out of 3 that at least during the current trial that HAPS can fail or can kind of be subject to an accident during mostly landing or takeoff. Do you think that we currently have or we will have in the future very accurate prediction of the, let's say, turbulence condition in the troposphere to minimize or like to eliminate, let's say, these accidents? And do we have actually in the world some spots, some nice spots where actually we have very, let's say, friendly troposphere from which we can land and take off?
Yeah, so I think there's a lot more to give from forecasting technology. It's always worth doing more research to improve forecasts, and what we're seeing now is a movement towards research targeting forecast products that are of benefit to these unusual aircraft, both fixed-wing solar planes when they undergo their hazardous flight through the troposphere to and from the stratosphere, but also forecast products targeting the lower stratosphere to help all types of stratospheric aircraft and balloon to navigate. However, knowing more about the weather is a great thing, but in the case of fixed-wing solar planes, it will make it safer, but it will make it even less available. You'll know very well when not to fly, or when not to descend, or when not to climb up. So for me, there are 2 things that have to happen to make them safer. We do need to improve weather forecasting, and that starts with better observation data gathering, for which the stratospheric platforms are a vital part of that. But there's also the need to improve their robustness and take advantage of new innovations particularly in fixed-wing solar electric aircraft, new innovations in expanding the operating envelope. You must be able to forecast conditions for which there is a very high probability that the aircraft will safely get to and from the stratosphere, and also to be able to improve situational awareness of weather data around the aircraft in the stratosphere so that it can understand its proximity to hazard in the troposphere. There are mechanisms for which hazardous conditions can propagate into the stratosphere and damage these aircraft. And so they need to be able to be forewarned of that and be able to be moved off station or away from the hazards. So all of that research is going on. I think we've got a really exciting end to this decade to look forward to, where I really genuinely think that the technologies will deliver and allow many of what's been talked about today to be fully commercialized in 2030. Thank you.
Very good. Thanks a lot. We are running out of time. I would like to thank all the panelists for their valuable perspective, their valuable contribution to this discussion. On behalf of all our students at KAUST, thank you very much. Thank you, Paul. Thank you, Halim. Thank you, Shiro. And thank you, Tom. And looking forward to meeting you in some of the upcoming conference to continue our discussion. Thanks.
Thank you. Thank you. Thank you very much.
Thank you.
Thank you very much.
Bye.
Well, thank you for Professor Salim, Mohammed Salim, for taking on this panel discussion for the panelists. I hope that was enriching for you. So please note that there is, for the checkout, there is a time window. Make sure you check out as early as you can. We'd really appreciate that. And with that, thank you and have a good night.